Welcome back to Beyond the Prompt. Today, we're diving deep into the inner workings of large language models with a fascinating new paper titled On the Biology of a Large Language Model.
That's right. This paper, and its companion on methodology, comes from Anthropic and tackles a core challenge in AI, understanding how these incredibly complex models actually do what they do. It's like trying to figure out the intricate machinery inside a black box.
And they lean into that analogy heavily, framing their work as trying to reverse engineer LLMs in a way that resembles how biologists study living organisms. Complex systems sculpted by seemingly simple processes. Evolution for biology, training algorithms for AI, producing incredibly intricate mechanisms.
Exactly. The big goal of mechanistic interpretability, the field this work belongs to, is to describe the transformations within these models in human understandable language. Think of it like wanting to understand the wiring diagram of the model's brain.
For listeners who might not be deep in AI research, why is this so hard? We know the model is made of layers of artificial neurons, right?
That's true, but those raw neurons are a big part of the problem. They're often polysemantic, meaning a single neuron can represent many unrelated concepts. This is thought to be partly due to superposition, where the model needs to represent more things than it has neurons, so concepts get smeared across multiple units. This makes looking at individual neurons less effective for understanding high-level concepts or circuits.
So the challenge is finding the right building blocks that are actually interpretable?
Precisely, and then figuring out how those blocks interact in sequences of computational steps, what they call circuits.
All right, let's shift gears now for our more technical audience. This paper presents a specific methodology for tackling this, detailed in their companion paper, Circuit Tracing. What's the core approach here?
The central idea is to use a replacement model. Instead of directly studying the original complex model, they build a simpler, more interpretable one that approximates parts of the original. Specifically, they focus on replacing the MLP blocks. That's multi-layer perceptron, which are a major source of nonlinearity and complexity, with something more structured.
And that something more structured is based on cross-layer transcoders, or CLTs.
Yes, CLTs learn sparse, interpretable features that replace the function of the MLPs. A key aspect is that these features are cross-layer, meaning a feature activation at one layer can influence computation at all subsequent layers. They found this simplifies the resulting circuits. Remarkably, they could match the underlying model's MLP outputs in about 50% of cases using these CLTs.
Okay, so they have these interpretable features in their replacement model. How do they then trace the computation for a specific prompt?
That's where attribution graphs come in. For a given prompt and target output token, they construct a causal graph showing the flow of information. The nodes in the graph represent things like prompt token embeddings, active CLT features, and the final output logits.
And the edges?
The edges represent the direct linear effects between these nodes. They designed their setup to achieve this linearity by replacing the nonlinear MLPs with transcoders and freezing attention patterns in normalization denominators from the original model's forward pass on that specific prompt.
Freezing attention patterns sounds significant.
It is. It simplifies the problem of tracing feature interactions via the OV circuit of attention heads, as these interactions become linear given fixed attention. However, it means their graphs don't explain why the model attends to certain tokens. The QK circuit is left unexamined by this method. This is a known limitation.
Right. So they get this complex graph of features and their interactions. How do they make sense of it?
They use techniques like pruning to focus on the nodes and edges that contribute most to the target output, and they manually group related features into supernodes to simplify the visual representation. This manual grouping and labeling of features was highlighted in our reading group discussion as a point requiring significant human effort.
Yes, I remember that. Someone drew a parallel to the difficulty of giving labels in topic modeling. It's a necessary step for human interpretation, but still quite manual.
Exactly. And once they have these simplified graphs, they form hypotheses about the model's mechanisms. They then validate these hypotheses using perturbation experiments in the original model, like steering or ablating features, and seeing if the model's behavior changes as predicted by the graph. The reading group found these intervention examples quite interesting, like the one involving suppressing features related to state capitals.
So, they applied this method to Claude 3.5 Haiku and found insights into various behaviors. What kind of things did they uncover?
A wide range, from multi-step reasoning like finding the capital of the state containing Dallas to Texas to Austin, to planning in poems where the model identifies potential rhyming words before writing a line. They looked at multilingual circuits, finding a mix of language-specific and language-independent mechanisms, though English seems somewhat privileged. They studied addition, medical diagnoses, how the model recognizes entities and sometimes hallucinates, refusal circuits for harmful requests, and even analyzed a jailbreak in the faithfulness of chain-of-thought reasoning.
They even looked at a model specifically fine-tuned with a hidden goal related to exploiting biases, and found features related to these biases were active universally in assistant conversations, suggesting the goal was tied to the assistant persona itself. That's fascinating. Using interpretability to audit potential hidden motivations.
It is. As the reading group noted, the paper tries to explain how we envision that the model must be thinking, and they actually found evidence for complex internal processes that we might expect, like forward and backward planning.
But the paper is also quite open about the limitations of their current approach. What are some of the big ones?
We already touched on the missing attention circuits, not explaining why attention patterns form. Another major one is reconstruction errors, the dark matter not captured by the CLTs, which shows up as uninterpretable error nodes in the graph. If the crucial part of the computation relies heavily on this dark matter, the graph isn't very useful.
And they struggle with understanding the role of features that are not active?
Yes, that's a key limitation. Their graphs highlight active features, but sometimes understanding why a behavior didn't happen requires understanding why certain features, especially inhibitory features, were inactive. Finding these inactive but relevant features is hard.
I can imagine the graphs can also just become overwhelmingly complex.
Absolutely. Graph complexity is a significant barrier to human interpretation, especially for longer prompts or more sophisticated computations. The manual work of pruning and creating supernodes helps, but it's time-consuming. Our reading group specifically mentioned the manual nature of grouping supernodes as a limitation for widespread use.
And features might not be at the right level of abstraction?
Right. They sometimes see feature splitting, where a concept we care about is split across multiple features, or features represent a conjunction of unrelated concepts. The supernode trick mitigates this for prompt-specific analysis, but makes studying generalization harder.
What about moving beyond single prompts to understand the model globally?
That's still a major challenge. While their method provides global weights between features that are prompt-independent, they found these global circuits harder to interpret than prompt-specific attribution graphs, partly due to interference effects. They did have some success analyzing global weights for arithmetic features, but it's not a general solution yet.
And there's the concern about mechanistic faithfulness. Are the mechanisms they find in the replacement model truly the same as in the original LLM, or just highly correlated?
That's a critical question. They validate with perturbations, but sometimes the results aren't perfectly consistent, suggesting the replacement model might take shortcuts.
So, given these limitations, what does the future of this work look like?
The authors are very clear that addressing these limitations is key. Future work needs to improve how they handle attention circuits, reduce dark matter, identify the role of inactive features, make graphs less complex, perhaps with better pruning or automation. They hope for a clear flywheel where discoveries inspire better methods, which in turn reveal more about the model.
And the potential for safety applications, like auditing for hidden goals, is a big motivator. But they caution that the current methods aren't reliable enough for a strong safety case yet.
Exactly. There's a significant chance they could miss something important, but they believe the work shows what the necessary level of understanding looks like.
They also emphasize the importance of tools and interfaces. Having an interactive way to explore these complex graphs is crucial because the raw data is too much. Our reading group appreciated the release of their interactive tools.
Definitely. Interpretability is ultimately a human endeavor, and the tools need to make the information accessible and trustworthy.
To wrap up, this paper introduces a powerful methodology, circuit tracing using cross-layer transcoders and attribution graphs, to peek inside large language models and understand their internal mechanisms on specific examples.
They successfully applied this to Claude 3.5 Haiku, revealing fascinating insights into reasoning, planning, refusals, and even hidden goals.
While the methods have significant limitations, particularly around attention, complexity, and coverage, the work provides a concrete path forward for future research in mechanistic interpretability.
It's a foundational step in reverse engineering these complex systems, much like biology seeking to understand life. The challenges are immense, but the potential to understand the nature of this new AI intelligence and ensure its positive impact is profound.
A truly insightful paper pushing the boundaries of what we can understand about LLMs. That's all the time we have for today on Beyond the Prompt. Thanks for joining us. See you next time.